Thanks very much for the invitation, Ian and Stephen. I've even heard you planned a major snowstorm for me over the weekend, so. All right, so I was accused of giving a generic title, too generic, but I hope it's not going to be too generic, actually. I'm going to talk about low-dimensional dynamics and hyperbolic free manifolds specific way. So first of all, this describes joint work done, different times with these people. Marcel, who's my student, who's supposed to be graduating very soon. Sylvain Bonneau and Toby Hall, who's an old-time collaborator. So the talk will do sort of three things. One is to introduce a generalization of pseudo-Anosov maps, and then call them generalized pseudo-Anosov maps. And the difference between these and usual Thurston pseudo-Anosov maps is that they are allowed to have infinitely many singularities, say on surfaces with infinitely many punctures, for example. And we might even go as far as dealing with densely many punctures or something, but I'm not going to do that for this talk. And so this comes up in the study of dynamics and the interface between one and two-dimensional dynamics. I'll sort of explain a little bit of this as we go along. And they, the way I first came across these things, we're studying families of self-maps of the interval or self-maps of the plane or the sphere, right? So this comes up they often come up in families. I'll talk about families here. So then we'll talk about the mapping tori associated to these generalized pseudo-Anosovs, and so one question that it's still kind of I'm interested in trying to answer it is whether or not it's possible to hyperbolize these things. Now there's a subfamily, so I'll talk about the specific family of generalized pseudo-Anosovs that come up in the study of unimodal, one-dimensional dynamics, and there's a subfamily of such generalized pseudo-Anosovs which are actual Thurston pseudo-Anosovs. So for these, there's Thurston's hyperbolization theorem that says that there are such the suspension or the mapping torus is a hyperbolic three manifold of finite volume, and so these sit there in this bigger family, and I will talk about these things and try to. And then there's some issues because these families are naturally parametrized and they are naturally continuous families of continuously varying maps. And in the world of finite volume hyperbolic three manifolds, there are no such things as finite varying families. And I see some yellow things on my. Are they on the slides or? Well, anyway, I didn't do this. Okay. Okay. So finally, circled in yellow, we'll try to reconcile the continuity of the dynamics picture with the non-continuity in the hyperbolic picture. Okay, so well, a generalized pseudo-Anosov map or a very generalized pseudo-Anosov map is essentially a pseudo-Anosov map where the foliations may have lots of singularities, infinitely many such, and perhaps even densely many singularities. Okay, so I'm not going to get into that definition because that's we don't need that here. But you would use some sort of an ergodic invariant measure to define an almost everywhere foliation and talk about transverse measures, and then you can kind of make up a definition that way. And these things do show up, and in some related context, but I don't want to go that far here. And we'll stick with a simpler definition, which is this. So I'll call, for this purpose of this talk, a generalized pseudo-Anosov map a self-homeomorphism of a surface, and you can think of S as a compact surface with maybe with infinitely many punctures, but the punctures which will occur, so as usual, the pseudo-Anosov map has two invariant foliations. The singularities of the foliations are pictured here, or at least the normal singularities are pictured here, and more prongs. I didn't put ... over there. But there may be infinitely many such, but they have to accumulate on some finite set, which I'm calling sigma here. And these foliations with transverse measures, they are stretched and contracted and stretched in this usual pseudo-Anosov fashion, and I can't erase this. Well, what it says here, behind here, that I can't turn off because then... I click what? Well, if I click the X, then it will exit, you see. Well, anyway. So can I click anything else? You think? Well, ay. Move the mouse. It doesn't seem to work, does it? Oh, anyway, so it's all right. Oh, there you go. All right. Okay. So if there are no accumulations of singularities, then we're back to the usual definition of pseudo-Anosov maps. Okay, so here's a picture of a typical accumulation of singularities, okay, that these things might have. And what I'm demanding is that there are only finitely many such things. Now, so I will show other examples. Well, actually, perhaps this is not the best didactic sort of thing. But generalized pseudo-Anosov maps are very easy to come by. I'll give more detailed examples in a second. I don't know why I put this undetailed example here, but in any case, so any Markov, so any graph map that lives on a surface that can be sort of so I'm writing unwraps on a surface here. So if you have a graph map on a surface that you can kind of unwrap on the surface, that is, it can be approximated by some sort of pseudo-isotopy of the surface. And if this graph map is Markov and has a irreducible periodic transition matrix, that being Markov just means that you have a graph and the edges of the graph map over other edges, completely over. There's no bending in the middle. Any such a map on any surface will produce, you can cook up a generalized pseudo-Anosov map according to the previous definition. So let me give two more specific examples. So here is one example of something that will lead to a generalized pseudo-Anosov map on the sphere now. Okay, so what I'm drawing here is a disk, which is a stylized disk, and the map on this disk just sort of squeezes it vertically, stretches horizontally, and maps it kind of like that. So this half disk here maps over here. This rectangle here maps over to there, and this third one maps over to here. Some here bends around, etc. It kind of maps like that. So inside of the rectangles, you just squeeze and stretch things, vertically and horizontally, and then you're allowed to bend, inside of the shaded regions. And then if you collapse vertical segments here to points, and these blobs to points as well, you get a graph map. Now this graph turns out to be the simplest possible graph. Is just an interval with marked points, and the marked points map, the first one maps to here, the second one maps to there, the third maps over there, and so on. So to such a graph map, you can associate now, so I'm not explaining in detail, but anyhow, there's a train track associated to such a thing, which is not an usual train track in the sense that it's not a finite train track, but it's an infinite train track. And the fact that this map maps edges completely across edges, or this one rather, means that this train track only has so it has finite amount of detail inside of these edges, and it's only around in the vertices where things perhaps are not as good as we would like them to be, that you have infinite amount of detail. But in any case, there is an infinite invariant train track, and from such a train track, you can build very much in the same way as you build pseudo-Anosov's maps out of invariant train tracks in the regular way. You can construct a map, a self-map of the sphere with a foliation that gets stretched, which sort of So the train track itself is like the unstable foliation, and then there's a vertical thing that you have to be a little more careful to construct, which gives this stable foliation. Okay? And then, so you construct a generalized pseudo-Anosov map of the sphere with this thing. Now, because the invariant train track is an infinite invariant train track, has got infinite amount of detail here, you end up having infinitely many 1- and 3-pronged singularities in this case. And it has 8 accumulation points of singularities. They come from, so the orbit of these points in the graph map here is this is a period 7 orbit. There are 7 points there that are mapped or permuted amongst themselves. And so these sort of correspond to the accumulation points here. And then there's one extra singularity sort of at infinity. And then there's this infinite orbit of 1-pronged singularities, which kind of marches out from infinity and then accumulates on these 7 accumulation points there. So this is a picture of the unstable lamination or foliation for that generalized pseudo-Anosov map. It's kind of hard to see, but the accumulation points are somewhere close to these bending bits, and there are 1, 2, 3, 4, 5, 6. Well, anyway, there should be 7 bending things in there somewhere, and this is a picture of the invariant unstable foliation. Okay, here is well, anyway, I can see it here. Anyway, so here's another example, in case you didn't like the previous example. Here's another example of how to build a generalized pseudo-Anosov. Take a square piece of square piece of paper with the horizontal and vertical segments to it, and then you do the identifications that I'm indicating here by these dotted lines. You just fold this bit of the square in half, you fold the top of the square in half, and over here you do something a little fancier. You just divide in half and fold the top half, divide in half again and fold it again, divide in half again and fold it again. Do infinitely many times. Do the same thing here at the bottom. Then it turns out that the topological space you get in the quotient is a sphere, and then the horizontal segments here become a foliation with singularities at exactly these dots over there, and the vertical segments also become a foliation. 2 foliations turn out to be invariant by the map that squeezes vertically by a half, stretches horizontally by 2, and then squeezes like this, stretches like that, and bends it over and places the square like that over itself. Okay? So this is a tight version or taut version of Smale's horseshoe map. Okay, but there's no wandering stuff here. Every point. The periodic points are dense, the map is ergodic, and the invariant measure is Lebesgue measure. Okay, so this is another example of, and then as you can see, so these 1-pronged singularities, they actually live in one orbit. So this point maps to this point, which maps to this point, this point converges here, and this this point comes from this point, which comes from this, which comes from that. So there's one infinite orbit of 1-pronged singularities. That there are no 3-pronged singularities anywhere, and there's one accumulation of singularities at the corner there. Okay. So that's I don't know, more kind of palpable example of generalized pseudo-Anosov. So another way one can think about these generalized pseudo-Anosov maps is as n-periodic homeomorphisms. I just put a picture here, but I sort of don't want to go there much at this point. But in any case, this is something that people care about. All right, so I talked about generalized pseudo-Anosov maps, defined them, and now I want to talk about families of such things.
So there's no standard picture around the accumulation point? You don't restrict it to be one of some finite set of pictures?
Well, at this point, I'm not doing this a priori, in particular because I'm at some point, eventually, not in this talk, but I want to allow for densely many singularities anyway. But the types of pictures that appear in these constructions are very specific, actually, are like the one I showed here, and then there's a more, so this is one type of picture you see. So this picture, when you actually draw the picture around here, there's a specific picture you can draw. And these are essentially the two ones that you see modulo sort of finite covers. Okay, so that's. Okay, families, okay? So in the study of one-dimensional dynamics, there's the so-called 10 family, which is very important. It contains sort of models for one-dimensional dynamics in a very, very general context. And in fact, this was proved, I think, between here and the university, Milner and Thurston, I think. So this family, this 10 family here, it's very important in the study of dynamics of one-dimensional maps. And what I've drawn here is the family of is the dynamically sort of important bit of the family that is more often drawn maybe like this. So you take piecewise linear self maps of the unit interval, say, and they have constant absolute slope. Okay, so this inclination and that one are constant or same absolute value, and then you vary this slope, and it goes from some point here where there's no dynamics to some very interesting dynamics as you get to the top of this family, and then the slope is 2. Okay, and what I've restricted here to the interval where the dynamics actually happens. So, well, anyway, so there's a piece around the left hand end of this interval where there's no interesting dynamics, and then you throw it out, and then what is left is what appears in this picture, and that's what interests us. So there's this family here which depends on this parameter which I'm calling lambda, and it varies between 1 and 2. Okay, for one, lambda is exactly equal to 1. You have the inclination 1 map here, which is not very interesting. But as soon as you get past that, you know, these maps have rich dynamics, and they're relevant. Okay, so as you vary the parameter lambda, the turning points, or these critical points of the tent map vary continuously from 1 all the way to 2, or from half to 1. And as they vary continuously, they might, so if you look at their orbit, this orbit might be finite or infinite. And there is some, and every time the orbit is finite, that is, every time the orbit either comes back to itself or falls exactly on a periodic orbit, you have a situation like the one I had before. You have a graph map. It's actually an interval map where you can divide it up into finitely many intervals, and these intervals are mapped across themselves. So we have a graph map, and we're back in the situation of building generalized pseudo-Anosov maps. Okay, so we have a graph map, which is Markov, that is, intervals map across each other, and you can therefore build a generalized pseudo-Anosov map associated to this tent map. In fact, the two examples I gave are themselves generalized. So I'll call these unimodal generalized pseudo-Anosov maps. Okay? Yeah.
You have these one-dimensional maps,
Yeah.
right? These tent maps, which you can write in that way or the other way. And then there's these generalized pseudo-Anosov maps, which are two-dimensional maps. And you're looking at these F lambdas are one-dimensional.
Yeah, I'm sorry. Maybe I introduce more notation than I should have. What I'm calling F lambda is kind of irrelevant. It's just the tent family. Okay.
Yeah. So they're one-dimensional maps.
They're one-dimensional maps. And if the critical point is got a finite orbit, yes, then you divide the interval up into that finite orbit, and then you have a graph, which is the interval, divided up into finitely many edges, which are the pieces of the interval, and they satisfy the Markov, partition thing that. And from this graph map, you build an infinite train track, and from the infinite train track, you build a generalized pseudo-Anosov map.
And you could do that for graph maps that are not just like on a line. You could do it for a whole bunch of
Yeah, that was the example I gave out of order. And you can do this anywhere. I mean, you know, I put one up on the torus. You can do this anywhere. Just take any surface, put a graph on it, you know, and then invent some sort of a self-map of this graph which has edges that map across, and be careful that the transition matrix is irreducible aperiodic, and build your own generalized pseudo-Anosov map. It's just a sort of a recipe then. Well, you have to apply the recipe, but anyway. Okay, so then we have the 10th family, and then for all these 10 parameters, the lambda parameters for which the critical orbit is finite, you can make one of these constructions. You can construct a generalized pseudo-Anosov map. Okay? And the parameters for which the critical point has finite orbit is a countable dense subset of parameters. Okay, so there's a countable dense subset of the interval 1/2 for which the critical orbit is finite, and therefore you can construct a generalized pseudo-Anosov map out of the 10th map. Okay? So I'm calling these guys phi sub lambda. So the f lambdas are just the 10th family, forget about those. But the unimodal generalized pseudo-Anosov maps I'm calling phi sub lambda, and they are parameterized by some countable dense subset of the interval 1, 2. Okay? So in the examples I gave before, so this example is one of those parameters there, and the tight horseshoe actually is also one of those parameters. So this is the parameter 2 at the very top of the family, and the previous the first one was parameter 1.686 or something. Okay? So, but you can build countably densely many such things. Okay, so let me show a picture. Oh dear, so am I going to be able to? I'd like to show a picture of how these invariant foliations vary as you vary the parameter. Okay, so let me see if I. So this is a motion picture of how these invariant the unstable foliation for these unimodal generalized pseudo-Anosovs vary as you vary the parameter kind of from 1 to 2, okay, or from more or less 1 to more or less 2. So that's the end. That's the last one. That is the tight horseshoe again. And does it look like it varies continuously? Well, it sort of doesn't, right? But the reason it doesn't. Well. Anyway, I'll talk a little bit about this. But the reason it does is that so the rounded part here is not really part of the foliation. It should really be understood as identification of the points in the bottom here with points at the top. It's just that I can't draw it too well. So anyway, we draw this in just to, but it should really be thought of as an identification. Okay, so that's why you're seeing these things. But the foliations themselves really should vary continuously, despite what the pictures might make you. Okay, believe. Okay, so what should I do here? Enter full screen. All right. Okay, so. All right, so we saw the family and how it varied, or the what?
Okay, never mind. I mean, it seemed like you skipped the slide, or maybe you went.
No, I went back because I didn't want you to read that yet. So there's this family, and I showed you a picture of the unstable manifolds varying as you vary the parameter. Okay, so there's this countable dense subset of 1, 2 for parameters for which I showed the unstable foliations for the associated generalized pseudo-Anosov maps. Okay, now I'm going to talk about the special subfamily of these generalized pseudo-Anosov maps, which happen to be on the nose Thurston pseudo-Anosov with finitely many singularities. Okay? Yes?
Lambda doesn't have anything to do with dilatation, right? It's just
Well, lambda is actually it is the dilatation, yes. It is a dilatation, yes. Or log of it, or e of it, e to the power lambda, or some, I don't know what you call dilatation. I don't know what I call dilatation, but it's some, it is, yeah.
Is it known something about dilatation of these generalized pseudo-Anosov maps, like discreteness or something?
those are a continuously varying family of dilatations.
Right.
But yeah.
Oh, you said that's exactly.
That's exactly it. Yeah. Yeah. Okay. Now, so now I want to talk about actual pseudo-Anosovs as defined by Thurston with finitely many singularities. So Toby Hall in his thesis in 1990 or something, actually, so much before any of this was done, he went and actually identified the exact parameter values for which. So this is not the way he phrased it, but in any case, what happened here up to now. So what Toby did in his thesis was to pick out from this family of generalized pseudo-Anosovs exactly the parameters for which you had an actual pseudo-Anosov. Okay? So and he identified a set of parameter values for amongst those densely many parameters, a subset of parameters that he called NBT, for which the generalized pseudo-Anosov map is an actual pseudo-Anosov in the sense that there are finitely many singularities. Okay, so this is some infinite countable infinite subset of the set of all those parameters lambda, for which the infinite train track in particular is finite. It's not infinite, it's finite. So this here is one parameter for which you have a period 5 orbit with invariant train track, which is a finite invariant train track. And from this train track, again, you can build the Thurston pseudo-Anosov. And because the train track is finite, there will be only finitely many singularities, and 5 one-pronged singularities, 1 3-pronged singularity at infinity, and this is a regular pseudo-Anosov. So I asked Toby what this parameter was this morning, and then he gave me this answer, and he still thought we would find it interesting to know that this number is almost exactly that. So maybe you'll find that interesting. I couldn't quite tell why there's any relationship between the two. In any case, so there are these normal. Here is the invariant foliation for that pseudo-Anosov, and besides the fact that it's much darker than the other pictures, there's one thing here that there are none of these bending these hooks happen within the sort of flat part of the foliation. All the hooks happen here or there or there or there. There are 5 spots where the hooks happen and nowhere else. And this is related to the fact that the foliation, the train track is finite, and this is an actual pseudo-Anosov map rather than generalized pseudo-Anosov map. Okay. So just to go back, so you have the 10th family, a continuum of parameters between 1 and 2. There's the set lambda, which is this countable dense set of parameters for which the critical orbit is finite, and therefore you can construct generalized pseudo-Anosov maps. And there's the set then of Toby Hall's parameters called NBT parameters, which is a subset of this countable dense set, for which the generalized pseudo-Anosov is pseudo-Anosov on the nose. Okay.
Andre, sorry, these are critically periodic maps?
So these guys might be periodic or pre-periodic. These guys are all periodic.
They're all periodic.
Critically periodic. Yes.
And so now magically this generalized pseudo-Anosov ends up being
A finite, a regular pseudo-Anosov. Yeah. There's.
Can you say, or are you going to say, like, which critically periodic maps this works for?
No, I'm not. so this is Toby's thesis, okay? So and there's no short answer to that. There's something very special that happens with these infinite train tracks. There's a miracle that happens, and it happens in some specific integers. There's got to do with Sturmian sequences. There's a whole yoga of things that go into here. But Anyway, so the set of Toby Hall parameters is an infinite countable subset of this other countable set, and it's infinite. It's got lots of accumulation points, obviously, but it's very far from being dense. Okay, it's a very sparse set there. Okay? And Toby and I have shown that the unimodal generalized pseudo-Anosov family is. Well, I showed you, the pictures aside from, the identifications is very continuous, and I'm sure it's the generalized pseudo-Anosov maps actually vary continuously with the parameter, but proving this is technically kind of difficult. And what we have been able to show at this point is that it is continuous at these NBT parameters and at the closure of the NBTs. Okay. Anyway, I'm sure it's continuous everywhere, but what I can prove at this point is that it's continuous on the closure. I should have said put a bar here. Okay.
By continuous here, you just mean that the unstable foliations converge?
Well, right. that you're starting to get at the difficulty. You have to prove that these. What I really mean is that there's a continuous family of spaces and a continuously varying self-maps of these spaces, and everything is continuous. But it requires, because these are identification spaces, you have to compare one to the next, and you have to make sense of all this. Okay, so. All right, so much for dynamics in dimensions. So let's go to three-dimensional manifolds. So the mapping torus of so UGPAs are self-homeomorphisms of a surface, and for this talk they have always been the sphere minus finitely or infinitely, countably infinitely many points. Okay, so then I'll take the suspension of these things and or the mapping torus associated to these things and start kind of what kind of three manifolds these things are. So if F is one of these generalized pseudo-Anosov maps, say a self-map of the sphere minus the one-pronged singularities, you could ask yourself what the suspension manifold is. Okay, so Thurston's hyperbolization theorem for fiber three manifolds says that if you have a regular finite, pronged pseudo-Anosov self-map of a surface, and you take the mapping torus associated to that, so that three manifold has a hyperbolic structure of finite volume. Okay, so there's in that, it's unique by Mostel, etc. And I think the same should hold for these generalized pseudo-Anosov maps. Okay, so if you take now a self-map of one of these infinitely punctured spheres, say the tight horseshoe, you puncture the tight horseshoe at that infinite orbit plus at the accumulation point, and then you do the suspension or the mapping torus of that. I think maybe you should be able to hyperbolize that is, put a hyperbolic structure there. But the ends of these things, you see, because you have one infinite orbit, when you take the suspension or the mapping torus of this thing, this infinite orbit becomes some infinite knot or infinite kind of braid maybe inside of this manifold, this three manifold. So you shouldn't expect finite volume. Okay, so you should expect infinite volume, but maybe you can hyperbolize it, and if if it works out the way it should, this infinite volume hyperbolic structure should be quasi-conformally rigid actually. So this is one piece of evidence I'll say quickly with what my student has been doing is that the way or a way to prove this hyperbolization theorem is to try and understand we have to prove the double limit theorem, and the double limit theorem deals with representations of the fundamental group of the surface into PSL2C. And the way the proof goes is that you're trying to show that some sequence of quasi-Fuchsian deformations of a given Fuchsian group, the sequence converges. Right? So then the theorem, you work a lot to show that if it does not converge, what happens? And what you prove is that if these quasi-Fuchsian representations do not converge in the world of quasi-Fuchsian of representations, they actually diverge, but diverge to something specific, and that something specific is an action on an R tree. Okay? So the point here is that because you have infinitely many punctures, these fundamental groups are infinitely generated. So these theorems, the way they have been proved, don't quite work, and because they shouldn't work for arbitrary infinitely generated groups. But these are specific infinitely generated groups where the infinity is kind of encoded somehow in the generalized pseudo-Anosov map. So they're sort of well-behaved infinitely generated groups. And for these quasi-Fuchsian representations, you can actually prove this sort of theorem here, which is a generalization of this work of Morgan Shalen, Bisfina, Paulin, Otal, etc., that says that if you have one of these infinitely generated groups associated to a generalized pseudo-Anosov map, and if you have one of these quasi-Fuchsian representations that are associated to this, well, either it converges, or if it does not converge, then it's sort of converging to an isometric action on R3. Okay, so this is just one important step in the proof, which you can actually generalize to this case. All right. Okay. So then let's go back to what is happening. All right. So going back to the story, we have the generalized pseudo-Anosov maps in the unimodal in the 10th family, and within this set, there's the NBT set, these special parameters for which you get on-the-nose pseudo-Anosov maps. Okay? So associated to the NBT parameters, the pseudo-Anosov map and its mapping tors, the associated mapping tors, has, by Thurston's theorem, a finite volume hyperbolic structure on the mapping tors, and I'm using m sub lambda to denote both the manifold and the hyperbolic structure. Okay, so the NBT parameters have associated mapping tori which admit finite volume hyperbolic structures. Okay, now finite volume hyperbolic structures do not admit deformations, so you shouldn't expect to be able to vary a parameter and see a varying family of finite volume hyperbolic structures. So as it turns out, when I first started kind of looking at these things, working with Sylvain Bonneau, and then Toby Hall got into the story as well, we discovered something kind of disturbing, that not only there's no hope that there's going to be any kind of continuously varying family, but sort of, well, I don't know if worse than that, but in any case, so we figured out that, for example, we proved that there are sequences of these Hall parameters, these parameters for which you can build finite volume hyperbolic structures, so NBT parameters. So, and these sequences, lambda sub k, depend on two integers. So you choose two integers, m and n, m is smaller than n, fix them, and then you can cook up a sequence of parameters in NBT, such that the sequence of parameters converges to 2. Right? All of these sequences go to 2. And then you construct the finite volume hyperbolic manifolds m sub lambda k. And these also converge geometrically to something, to a finite volume hyperbolic 3 manifold that I'm denoting by n. Now this n, this limit here, depends on the two integers you chose. And these limits turn out to be infinitely many. They depend on the integers m and n, and they're all different. So the parameters converge all to the same parameter, namely 2. Remember that 2, in fact, is the parameter associated to the tight horseshoe, as it happens. So all these sequences converge to 2, and then you build the hyperbolic finite volume hyperbolic manifold associated to those parameters. You take the limit, and they all converge to hyperbolic 3 manifolds. And depending on the coprime integers you've chosen, the hyperbolic 3 manifolds are all different. Okay?
What way do they converge? Algebraically?
Geometrically.
And do you choose base points in some clever way?
No, I think. Well, I suppose you have to choose.
If you choose, they still converge?
Well, I think if you choose them kind of not cleverly, then they might not converge. But I think almost any way you choose them, it should.
Yeah, you want injectivity rate is bounded
Yeah. But,
Hopefully you'd say that except for like the
yeah.
connected.
If
If that's so, right, then it should converge.
Yeah, if you do something kind of dumb, you may, but find yourself get into trouble. But, all right. All right. So the point here is that by this theorem that I mentioned, so the family of generalized pseudo-Anosov maps of the surface, that is of the sphere, they vary continuously. So all of these pseudo-Anosov maps are converging to the same thing, which actually is the tight horseshoe, right? Whereas the suspensions are converging to infinitely many different three manifolds. And let me just show. So for example, if you choose the co-prime integers to be 0 and 1, the limit is the magic manifold. Right? If you choose the co-prime integers to be 1 and 2, then it's converging to something that has volume 6.552. It's probably some manifold in the census. I don't know which, but in any case. So and here's a plot of these volumes as if you parameterize them by m over n. So here's m over n, and these are the volumes of the things that you see of the limits. Okay, so this is the magic manifold here, and then you see lots of things. And as you can see, you can think of taking limits of limits as well, right? Anyway, so. So these, I think so, but I think so. It's a bit tricky to know exactly what it is because started getting. Well, the reason that this theorem is so the reason here is that you're doing twists around. So what is happening here is that you're doing twists around some simple closed curve, and then you're creating cusps. That's essentially what's behind here. Okay. Yes.
Somehow you're getting a series. You're saying there's a sequence for each mn without really saying anything about the sequence.
Well, the sequence is this I think n over k n plus m. But it's not this sequence. It's it's some sequence associated to this. I would have to explain to you more than but. No, this. Yeah. So associated to this rational, there's a way of cooking up an eating sequence. Okay. So and the way to associate this, so associated to rationals, there are Needing sequences, and these are the Needing sequence of the unimodal, the associated unimodal map. Okay. The slope is a little less clear what it is, but this association here is easy to explain what it is. All right. So. Okay, so I'll finish with a question, which is the following. So in this world of finite volume manifolds, you cannot hope for continuously varying families, right? I mean, just it's not the thing. Right? But if you start doing generalized pseudo-Anosovs, then you start having to deal with infinite volume three manifolds, and then maybe you have some hope of building continuously varying families. And perhaps this is it's kind of maybe kind of bridging the gap here, or kind of fixing this continuously varying problem for in this context. So if you look at the unimodal generalized pseudo-Anosov family, then instead of believing in these miracles that Toby kind of figured out in his thesis, you should really, instead of looking at the pseudo-Anosov, you should look at the completion of the generalized pseudo-Anosovs that happen elsewhere. And then if you take this completion, then everything is generalized in the sense that there are the infinite orbits for all of those parameters. And then all of those surface maps would have infinitely many punctures, and then all the suspensions would have infinite volume hyperbolic structures, and that might actually kind of fix this this problem here, but I haven't got that far. Okay, so if all this holds water somehow, you would end up seeing. So in the cyclic cover, you would see the ending laminations of these cyclic covers would then be those pictures that I showed. Right, you would see see this inverse limit of the unimodal family as those ending laminations for these things. Okay, so I guess I ended before schedule or something.